All right, so here's the video lecture on the central limit theorem. And I know you don't know what that is just yet, but you very soon will. The central limit theorem is important to study because we use it a lot in the second half of the course. So for a lot of what we do in inferential statistics, this is the theoretical foundations of it. So if you remember, we talked about random variables before. And we said that a random variable is a variable that the value changes based on the particular sample we take. Every random variable has a distribution, a mean, and a standard deviation. Now remember that x bar depends on the particular sample we take. So if we take a different sample, we get a different sample mean. Therefore, it's a random variable. So that means x bar itself has a distribution, and that distribution is called the sampling distribution of x bar. X bar has a mean, and x bar has a standard deviation. And the central limit theorem is what tells us the distribution, the mean, and the standard deviation of the sample mean. So if we were to take a sample of size n from a distribution, any distribution, that has a mean mu and a standard deviation of sigma, keep in mind the sample mean could take on a whole range of values. Some would be more likely than others. The mean of that distribution of x bars, instead of calling it mu, we call it mu sub x bar, just to differentiate it from mu. And the standard deviation of x bar is sigma sub x bar. Okay, so now for exactly what the central limit theorem says, it says that the distribution, the mean of the distribution of x bar is the same as the population mean. And this shouldn't be a surprise, because if you take a sample mean, you expect that it's going to be pretty close to the population mean. Sigma sub x bar is not quite so easy. It's not the same as sigma, it's a little bit smaller. So think of it this way: if you've got a distribution of individual values, that's going to be more spread out than the distribution of a bunch of sample means. Because every time you take a sample mean, it pulls in those extreme values. So the distribution of a bunch of middles is not going to be as spread out as the original distribution of values. And it's smaller by a factor of the square root of n. So if they're asking you to use in a problem sigma sub x bar, all you have to do is find sigma for the original distribution, divide it by the square root of the sample size. And we also know that x bar follows approximately a normal distribution as long as one or the other of these, or both, is true. First, we need the sample size to be large. And when we say large, usually the cutoff is 30. So anything greater than or equal to 30, we consider to be a large sample size. So if we have a large sample size, automatically we know x bar follows a normal distribution. Alternatively, if we don't know that, but we still know that the original distribution being sampled follows a normal distribution, we can still say that x bar follows a normal distribution. And if we know both of those are true, that's that much better. So just in summary, because I think this helps, the original population being sampled has a mean of mu, standard deviation of sigma. It might follow a normal distribution, but it might not. And we have n items being sampled from this distribution. Now, if we're looking at the distribution of x bar, in other words, the sampling distribution, that has a mean of mu sub x bar, which happens to be the same value of mu. It has a standard deviation, sigma sub x bar equals sigma over the square root of n, and it follows a normal distribution as long as either the sample size is large and or the population being sampled follows a normal distribution. And by the way, how would you know that the population being sampled follows a normal distribution? For our purposes, you'd have to be told. So you'd see at the top of a problem, it would say, assume this follows a normal distribution. So in those problems where we know that X bar does follow a normal distribution, that's nice because we can use the normal distribution to find probabilities with X bar. So for example, if we suppose, like we did in the previous lesson, suppose that the high temperature in June follows a normal distribution with a mean of 80 degrees and a standard deviation of 4 degrees. Suppose we randomly sample 20 days in June from the past 50 years, and we consider that we're calculating the mean of those 20 days. Does that sample follow a normal distribution, the sample mean? Yes, because even though we only have 20 days, so that's a small sample size, an N of 20, you're still told the original distribution is normal, say normally distributed up here. So we can still use the normal distribution for X bar. So what would be the mean and standard deviation of X bar? Well, mu sub X bar would be mu for the original population. The original population had a mean of 80. So mu sub X bar is 80. Sigma sub X bar is going to be sigma for the original population, which was 4, over the square root of the sample size, and we said the sample size was 20. Therefore, sigma sub X bar is 0.8944, because that's 4 over the square root of 20. Okay, so now we can use that to find a probability. So if we wanted to find the probability that the mean of the sample of 20 that we took is between 78 and 82 degrees, that would be probability 78 less than X bar less than 82. So in the last section, when we needed to convert X to Z, we subtracted mu and divided by sigma. But now we want to convert X bar to Z. So we're going to use almost the same formula, but instead of subtracting the mean of the X's and divided by the standard deviation of the X's, now we've got X bars. So we're going to subtract the mean of the X bars and divide by the standard deviation of the X bars. So for this problem, to convert 78 and 82 to Z, we've got 78, which is what we're trying to convert, minus mu sub X bar, which is 80, divided by the value of sigma sub X bar we found. When we do that, we get negative 2.24. And we'll do the same thing with 82, subtract mu sub X bar and divide by sigma sub X bar, and we get, for those two values, negative and positive 2.24. And now if you look on the Z table to find the probability between those two numbers, you'd look up 2.24. First, you'd find the area to the left of it and get 0.9875, and then subtract the area below negative 2.24, and that's 0.0125, and so you get 0.925. Okay, so what that tells us is that there would be a probability of 0.975 that a sample of 20 from that population would be between 78 and 82. Okay, so that's our answer to that problem. If we look at another example, suppose we have, we're looking at large schools, and we have the mean number of people who withdraw from intro stats courses is 18 with a standard deviation of 4.2. And we take a sample of 36 classes. And we want to find the probability that that we would, if in a random sample of 36, get a sample mean of more than 20. So we want to find, in other words, probability that X bar is greater than 20. So the first question we have to ask is, Does it follow a normal distribution? It being X bar. Well, in this problem, we have not been told that the original distribution is normal. That means that we have to look at the sample size. But as long as the sample size is greater than 30, and it is, because we have a sample of 36, then we can still use the normal distribution. So now that we know that, we need to find the mean and standard deviation of X bar. Well, we know that mu sub X bar is the same as mu for the original population. Well, they told us that was 18. And sigma sub X bar is the standard deviation of the original population, so that's 4.2 over the square root of 36, because that's the sample size, and we get 0.7. So now if we want to find the probability that X bar is greater than 20, that's a typo there, X bar should be greater than 20 there, we need to convert to Z. We take 20 minus 18, that's mu sub X bar, over sigma sub X bar, and we get 2.86. And if we look at the Z table, we get that the area there is 0.0021. Okay, so that's the answer to that problem. So would that be unusual? Remember that that cutoff of 0.05, where it's, I think they call it the rare event rule. Any probability less than 0.05 is small. That probability was 0.0021. Therefore, yes, that probability is small. Therefore, that would be an unusual event. All right, so that's it for that lesson. I do have some more examples in another video, and it would probably benefit you to watch those as well. All right.